Hello, and welcome to our talk, Two Become One, One Becomes Two, Attacking and Protecting Two-Factor Authentication. We're happy to be here, even if virtually, in PasswordsCon 2020. Great being here. And my name is Tal Beery, and I'm a co-founder for Zengo, developing a secure and easy cryptocurrency wallet.
And I'm Alex. I'm a security and blockchain researcher at Zengo.
Yeah, and as I said, Zengo, we're a startup, VC backed. We're doing an easy and secure crypto experience from the mobile device, and soon you'll find out how it's all connected to two-factor authentication, the topic of this talk. So what are we going to talk about today? We'll start with a very brief intro to two-factor authentication, universal second factor, U2F, and web authentication, motivation, and how it works. Then we would explain why hardware solutions are not solving it all because of confidentiality, availability, and user experience issues. And then we will connect, as promised, the worlds of crypto wallets and two-factor authentication, and show you how the way we solved this very similar issue with cryptocurrency, such as Bitcoin and Ethereum, very hot right now, and apply these solutions to the field of two-factor authentication and universal second factor, U2F. And we'll conclude with some next steps and questions and answers. So let's start in the beginning, the motivation. As you all know, you're here in PasswordsCon. There are many security issues related to passwords, and in fact, passwords are to blame in many of the breaches, as every report, security report mentioned. For example, Verizon's report from this year. And one of the biggest problems with passwords is that humans are not very good with secrets. We're not good in generating secrets. We generate guessable passwords. We tend to reuse passwords, and we're not good in protecting this secret. For example, if we are presented with a phishing website masquerading as the real one, there is a good chance that we will be indeed tricked and will give in our password to these masquerading sites. So to solve that, we might want to replace humans with machines. And because machines are better than humans with secrets, they're better in generating them because they can generate a very long random key for each site, and they're not getting tired out of it, and do not reuse the same key for different sites. They're better in protecting them. They're not confused by visually similar sites, and they know how to do crypto, so they can use other protocols in order to defend against other attacks, for example, man in the middle. Additionally, as computers know how to do crypto, we can use public key cryptography, and using private and public key, we can give this, as a user, give the service we're going to authenticate to only our public key, just public information, and not surrender some secret information to it, such as our password. And finally, private key can be stored on different hardware to reduce malware-based theft. And notice that we counted quite a few benefits for doing authentication with machines and not humans. And only in the last bullet, we mentioned hardware, because every other aspect of it is completely, can be completely implemented either in software or in hardware. But to enable all of this goodness and put it to work, machines require standards, because as humans, just give us a text box and write password by it, and we'll know what to do. But machines require some better standards than that. And luckily with standards, there are so many of them, but the important ones are web authentication that standardize the interface between web applications and the clients. Usually they call it web application relying party, as you see in the diagram below. And also and there's the universal second factor, U2F, and that standardized the interface between two-factor authentication and the client, the computer and the browser. So with these standards, the web application does not need to know each and every implementation of the device. So devices, browsers, and web apps can work together. And this indeed drives some mass adoption in this sector. So there are quite a few 2FA vendors supporting it, browsers, leading browsers such as Chrome, and others, and web apps that support that. For example, Facebook, and we'll see a demo of it in the end. So it's already working. And just a small dive into the technical details, and Alex will elaborate on that more. What happens behind the scenes? User generates a key pair, private and public, with the U2F device. A user registers their public key with the service using the interfaces supplied by U2F and web authentication. And when authenticating, the server sends a string for the client to sign. It's called challenge. The client signs that challenge using the U2F device and supply it to the website. Then the website can validate and verify this signature using the previously registered public key. So what it means, we can derive already requirements based on this high-level description of two-factor solution. The requirements are as follows. The solution needs to generate a key pair, private and public, send a message with a private key, understand the protocol to generate messages and to validate messages to be signed, keep the private key secured as it enables full control. This is security requirement, because if the attacker obtains the key, now they have the same capability as the original owner, and which puts us back in the situation where password stealing key is like stealing a password. So, and when that happens, two factors becomes effectively one, and we are in one of the original problems we set out to solve. So we're saying one of the way we're securing 2FA is by using hardware. And usually we say hardware is more secure than software. But in fact, when we look into the details, it's not so true. It's true that confidentiality is better with hardware than in software, because hardware better protects their secrets. It's harder to extract, for attacker to extract the secret from hardware than from software. But not impossible, as the links there show. There are physical attacks, vulnerabilities, etc., that still enable attackers to attack even hardware 2FA implementation. So when we usually say hardware is more secure than software, we mean confidentiality. However, there's a very important aspect of security, which is availability. And in that sense, software is much better than hardware, because backing up keys in software is very easy. But what happens when you lose your hardware token? If you don't remember where you put it, or someone stole it, or it just got broken, what do you do now? No easy solution for that. And additionally, besides security, there's a very important aspect of user experience, when some would argue it's even much more important than security. And in this aspect, software is much better than hardware, because user experience, people don't want yet another thing in their pocket. They don't want more hardware in their pocket. And for example, how do you share an account with multiple people with hardware, especially in a current scenario of COVID-19 and working from home? Let's say two people had shared account, but when they were in the office, it was very easy maybe to move the physical key between them, but now they are miles apart. How that happened? Additionally, there's the cost issue. hardware cost is much more than the zero cost of password or software. And the experience of replacing something that you used to get for free and now you have to pay something to buy this token, it's very bad experience for user. As a result, it should come as no surprise, for example, that Google finds that only 10% of Gmail users are unable to factor authentication. Why is that? Because the user experience is not as good. And to solve that, we will first talk about the insight we had that cryptocurrency wallet has pretty much the same requirement as 2FA. So let's see what cryptocurrency wallet needs to do. The requirements are very much the same. The wallet needs to generate a key pair, private and public keys, sign a message with the private key, understand the protocol to generate messages or validate messages to be signed, and keep the private key secure. And this insight, we cannot claim we first thought about it. And for example, important thought leader in the field of cryptocurrency, Balaji, already said in 2019, the password management, private key management, and crypto wallet will eventually converge. And the reason behind it that they are performing pretty much the same tasks. And hopefully by now you are convinced with that. So how did we solve these very same issues with Zengo, and what makes Zengo crypto Zen easy and secure? Well, the most important building block for that was threshold signatures. Threshold signatures is a cutting edge cryptography researched in the academia. And using threshold signatures, private key becomes distributed and no longer a single point of failure. What it means to be distributed? It means that there are back and forth messages exchanged between the different parties. And key generation now becomes each party creates a share, which is not half of the key. And to sign, they do some kind of message exchanges or a ping pong dance, as we like to call it. And together they are able to sign in a way that they are not, of course, revealing their secret information to each other, just exchanging messages. And in the end, the signatures looks the same as the one that would have been created with non-distributed monolithic protocol. So when one becomes two, when a single private key becomes two shared, it's harder for the attacker to steal because they now need to compromise two different platforms in the same time. And also easier to back up because each share is meaningless by itself. And as a result, in the past, you had a problem to back up because it was just a private key. If you back it up, you create more attack surface for attacker to steal from the backup. But now that you're backing up shares, that each of them is meaningless on its own, then it's far more easy to securely back them up. And that's exactly what we do in Zengo, in our wallet app, available in app stores. We are the first keyless wallet, no more single private key, but a distributed private key. The security of it, the confidentiality is realized using two-party threshold signatures, with Zengo server is one party and Zengo app on the user device is the other party. And each share is stored in a secure manner. For example, we utilize the device specific hardware security models, for example, a secure enclave in iOS, iPhone. And availability, each party, the app, the coder is backing up, making sure the share is backed up to the cloud solution of the user and the cloud solution of the server. And as we said, one of the most important aspects is the user experience, and the user experience that we found out that people love is mobile app, because mobile devices are already in the pockets of customers. So no additional hardware in the pocket, and also no additional cost, just download it from the App Store for free. And how all this goodness is applied to U2F, Alex will explain.
Great. So thank you, Tal. And now I'll take you on a journey of how we implement U2F with our threshold signatures. Again, a reminder of how the U2F protocol flow works in general. So there are three parties involved in the protocol: the website or the service that the user wants to connect to, the browser that it uses to connect to the service, and the USB key or security key that's doing the secure authentication. So first of all, there is a key generation process, a registration process, where they all agree on a set of public and private keys that the user then needs to use again in order to authenticate. I won't get into the registration process itself, but once it is complete and the public key is established, now the user wants to connect and use the service. The website sends a challenge to the browser. The browser augments the data with the URL, and there is also a nonce there. And this also helps us prevent man-in-the-middle attack and phishing attacks from by adding this information. This information is moved to the path to the USB key, which is doing the signing. Once the message is signed, it is forwarded back to the browser and to the service. And if the service indeed sees that the signature matches the public key that was agreed upon, then authentication is complete and the user can log in and use the service. So in order for us to do this via threshold signatures, the first step was to replace this USB key with some software daemon. So there is nothing magical or special about doing this via USB. There are benefits and trade-offs, as Tal touched upon, but eventually it's doing public key cryptography. So the first step was to run a service on the end user's device that will do the signing. Now, this of course is not perfect, because if the service is running on the device itself and you already have autofill for your passwords, so there is not much to do for an attacker that's able to steal your device, and it's a problem for security. So the ultimate goal is to replace that with the Zengo app, which will communicate with the Zengo server, and together will generate the signature required. And we will now see exactly how this happens. So one of the main building blocks that we use to make this possible is our open source Gotham City library. So this is part of our stack of libraries that we use in our product. Gotham City has a server side and a client side, and where the server is operated by us, by Zengo, or an operator, and the client side is on the end user's device. The server side offers a RESTful API through which the client can make requests, and together they do the key generation and signing in order to generate keys and signatures. Now, currently, Gotham City supported the ECDSA and EDDSA curves. These are commonly used in many cryptocurrencies and blockchains, and specifically because U2F requires a slightly different signature scheme, namely the P256 curve. We added that, namely Oded added that for this project specifically to make this work. Now a little bit on Gotham under the hood. So we said there is a client side and the server side. Again, the client side and together they keep their key shares. The client side keeps the key share on, for example, a secure enclave or on the keychain or some secure device. On the server side, the key share is kept, for example, in an encrypted database. And it is important to note here that the server side is not a signing service. It's not that the client is requesting the service just do the signing for me. They need to work in tandem. They need to work together in order to both generate the key and create the signature in this ping pong dance. Now, this process of, as we have seen, so U2F is public cryptography, and this is something we're familiar with. We have a wide variety of blockchains, each with their own quirks and features of what do you need to sign, how do you need to sign, the curves that you need to use in order to complete this. So this is a process that we are accustomed to. So the general recipe of how you take a public cryptography service and turn it into a threshold signature scheme with Gotham in our stack is the following. We start with some single party implementation, make sure that it all works, and basically replace all the cryptography with our cryptography. So, for example, identifying where key generation happens, what kind of curve is required, etc. Then identifying what kind of data needs to be signed, what needs to be sent back and forth, and finally replacing the calls instead of to the single party signer or a USB key with calls to Gotham. And the similar process was applied here. So we started off with Rust U2F, which is an open source library, which offers the U2F implementation on the end user's device. It simulates a USB key, and this is how this is where we started from. The library is implemented in Rust, just like the rest of our software stack, which made it relatively easy to do a native integration with our stack and with the added benefits of Rust as a secure language for cryptography and security. The implementation worked on Linux via USB, again simulating a USB, and the proof of concept that we'll show here works on Fedora, and we're going to see that in the demo soon. So again, basically we took that and replaced all the cryptography with ours. So replacing key generation and signing with Gotham with the 256 curve that we added. This library, as well as the rest of our stack, is available and open source. You're more than welcome to go and try it out and see that it indeed works. Now, a little precursor to the demo that we'll now see. So U2F is supported across a variety of services and websites. Dear to our heart, our blockchain exchanges, and Coinbase is one of the more popular ones. We'll see how we do registration with U2F, and then authenticating and logging back in, and finally see what happens after we stop the services and restart them again. So now for the demo. I'll pause the demo here for a second and explain what we are seeing. So on the left, there is a Coinbase where we already created an account, registered with a username and password, and now we are trying to register a second factor for extra security. On the upper right is the Gotham client. This is what's running on the end user's device. And on the bottom right is Gotham server, which of course can run remotely and receive requests from the client to create keys. Now, our user will begin the registration process. We'll start the services. The user will be prompted to do some to enter some live signal, which is this approve request, just like tapping on the USB key. And as you can see, messages begin to run between the server and the client. Several messages. It is a dynamic protocol to create the signatures, and once it is complete, the key shares are stored on each on each part. Right. Next, we'll log out and try to log back in. Again, the user is prompted to give some liveness signal, and once they do, messages are exchanged between the server and the client, and success. The user is successfully logged in. So yeah, that's pretty cool. So just to show you that there is no trickery involved, we'll log back out, stop the server and the client, and attempt to log back in. Now, since we haven't registered a USB key, we'll be prompted for one, but we will not get the request from the Gotham client. And only once we restart the service, we will get the message again, and we'll be able to log in, just to show you that it works across sessions, across logins, etc. So this is very cool. And do note that there were no special modifications that were required on the browser side or on Coinbase side for this to work. The signature that's created is indistinguishable, and because we are integrating to it via USB, no special additions were required for us to integrate this U2F service. Now, this is not perfect yet. It works over a VM. There are more to strive for, and Tal will continue on that and elaborate and sum up.
Thank you, Alex. What a great demo. It's like con days in sports when someone scores a goal and you don't hear the crowd roar. It's like suddenly miss the claps and the hand clapping after a great demo, but it is what it is. So as Alex showed, we already have the main building blocks for implementing U2F using threshold signatures. And the missing part is, of course, browser integration. Rust U2F, the infrastructure we use, just mimics USB events in software. But there should be better support in browsers. So currently, originally, Bluetooth interface was supported, so it would have been easy to do with a mobile app that has Bluetooth support. However, it was removed because problems with that. But we talked to Google guys, and they said Bluetooth will be re-added next year, 2021. So we hope that happens. And we can always fall back to using extension. For example, Krypton, you can try it out. It's a software U2F that just add this functionality via a web extension. But of course, this is just software U2F. It's not a threshold signatures. So let's sum up what we learned today. We learned today that U2F, or universal second factor, is great for the security of authentication. It's certainly an upgrade. However, hardware solutions are not perfect. They have issues on confidentiality, availability, and most importantly, user experience. We can use the knowledge we learned from crypto wallets that has the same tasks and the same issues and apply this solution to universal second factor, U2F and 2FA, by using threshold signature and get the best of both worlds. So with that, we conclude. This is the way to contact us. And now we'll be taking questions.